for the last talk of the HoTT-UF.
Okay.
Wind is going to talk to us about sorting.
Yes. Okay. I'm an undergraduate at the University of Glasgow, and I'm going to talk about some results that I formalized with my supervisor Vikram and also my professor Dr. Simon Gay. So I want to start off with a very simple question about sorting. So consider, okay, so imagine with a bag of three colors, red, white, and blue. Now, how many ways can we sort an unordered list of such balls into the Dutch flag? Well, obviously, there's only one way, which is given by the order red, white, and blue. But what if we also want to consider other flags? Well, we might consider how many ways we can sort our bags of balls. And we know that there are 3 factorial, so 6 permutations of red, white, and blue, so there's only 6 possible orderings we can define. And we say that because there's exactly 6 orderings, we can only define 6 correct sorting functions. And we want to go one dimension higher and say that there is an isomorphism from orderings to sorting functions. So sort functions are basically just a subset of functions from unordered list to list. And in order to prove such an isomorphism, first we need to formalize what unordered lists and lists are. And then we need to lay down what the subset sort is. In other words, like what is a sorting function satisfy that normal function from an unordered list to list doesn't. And finally, we want to construct our full equivalences. So we're going to use both category theory and type theory because category language allows us to describe universal properties of free algebras, which as we will see, we are going to use free commutative monoid to describe unordered list and just free monoid to describe list. And also we use cubical actor type theory to construct these free algebras. So I want to give a quick, very quick overview of universal algebra. So in universal algebra, we have a signature, which is just a set of function symbols and an arity function saying how many, denoting the arity of the functions. So this would give us a signature endofunctor, which is just a sigma type of the function symbol and a tuple of x, which is determined by the arity of the function symbol. And with this, we can define what a F sigma algebra is. It's just a carrier set X and also an interpretation function or an algebra map that takes a function symbol and an operand and it maps it to elements of X. With this, we can define what a homomorphism is and F sigma algebras and their homomorphism will form a category sigma algebra. So for example, the signature of a monoid had the identity function and the multiplication function. So the identity will have arity 0 and multiplication with arity 2. And then we can define what a free sigma algebra is. So a free sigma algebra is essentially given by a type constructor F and an inclusion map. And finally, it needs to satisfy the universal property that post-composition with eta would be an equivalence. So what this means is that given a homomorphism from fx to y, we can map it to a unique set function x to y by just composing with eta. And the inverse of this would be the extinction operation. We're going to use sharp to denote this, which just maps a set function x to y to a homomorphism fx to y. And we can define the carrier set of this F sigma algebra by a tree. So the leaf of the tree would be just elements of the underlying type. And the branches would be named by an operation symbol, and the number of children would be determined by the arity of the operation. Now, this leaf constructor would be our algebra, would be our inclusion map. And the node constructor would be our algebra map, and with this we can just say that yeah, it is the free sigma algebra on free. So here's a diagram for what a tree would look like. As you can see, it's basically just an abstract syntax tree of a sequence of algebraic operations. Now, because we are in this example, we are dealing with monoid, and by associativity, these two trees should be equal. But we haven't defined any equations yet. So in our framework, the way that we defined equational the way that we define equation is as follows. So first, we again define an equation signature, and which is given by a set of equation symbols and also a function denoting the arity of the equations. So again, we will also have a signature and a functor, and we can define a system of equations as a pair of natural transformation left and right from the signature and the functor to a tree. In other words, say X satisfies a system of equation T if for every assignment row sharp would co-equalize left and right. More concretely, what this means is that row would assign three variables to a concrete element of X, and row sharp would just evaluate a tree given an assignment of 3 variables. So as an example, monoid would have the equation symbols unit left, unit right, associativity, and the arity of unit north is 1. The arity of associativity would be 3. To prove that natural numbers satisfy the equations of monoid, we just need to prove these equations. And the sigma algebra satisfying theory T would form a subcategory sigma epsilon algebra. And we just say that sigma epsilon algebra is free if post-composition with either is an equivalence. Now, in our work, we only consider special cases for monoids and commutative monoids. But one very natural question we might ask is if we can construct any arbitrary free algebras. Now, due to BLAST, we need choice to handle infinite arity operations. So we didn't go that route. And also, we tried to define an arbitrary free algebra for finitary operation, but then we ran into some strict positivity issue in cubical actor. So we didn't really investigate further, but it should be possible. Now, let's give some example construction of a free monoid and free commutative monoid. So this is well known that it's free monoid, and we can turn it into a free commutative monoid by 2 ways. So the first one would be just using a path constructor, making it a high inductive type. So this is basically just the finite multiset, which Forsten talked about yesterday. And another way, we can just quotient it by permutation relation. Now, another common construction of free monoid would be the array. So again, we can just quotient it by relation. So here, our relation just says that there exists an isomorphism, or there exists a permutation on the index that would make 2 arrays equal. And we kind of notice a common pattern. So for both PDIS and back, we are just quotienting a free monoid and turning into a free commutative monoid. And we may ask, is there a very general way we can turn a free monoid into a free commutative monoid by quotienting? So, and if that's the case, what properties do the relation need to satisfy? So here we introduce the notion of a permutation relation. And we say that a relation is a permutation relation if it's an equivalence relation, if it's congruent with regards to multiplication, and also it's commutative. And finally, and most importantly, it respects sharp. In other words, for any function f, if a is related to b, then f sharp a should be equal to f sharp b. Now, as an example, so in order to prove that back is free commutative monoid, we need to prove that the relation satisfies commutativity. So in other words, there exists some permutation on the index that would make f plus g equal to g plus f. And we can do this by just partitioning the index and then just swapping it. And since it's just a series of elementary permutation, isomorphism, so it will only be natural that the resulting phi would also be an isomorphism. Proving that the relation respects sharp is more complicated, I'm going to give a very high-level overview of the proof. So first, notice that if the permutation fixes 0, then we can just prove this by induction, because if it's fixed as 0 by pigeonhole principle, then we can just get a smaller permutation, and by induction we can get rid of the smaller permutation and the proof is complete. But in order to generalize this to any cases, what we first do is to take the original permutation, and then we construct a new permutation such that this new permutation fixes 0. And it's designed such that it is very easy to prove S sharp on array applied to the original permutation would be equal to S sharp on the array applied to this new permutation. And the way we did this is to just define this new permutation as follows. First, we apply the original permutation, then we partition as 0. We swap it so that 0 is moved to the left. And now this new permutation just fixes 0. And because we're just doing elementary swapping, then by commutativity, we can easily prove that S sharp on I applied to the phi and S sharp on I applied to tau would be the same. And finally, we can just complete the proof. We take the original permutation, and then we turn it into this new permutation. By induction, we just complete the proof. Okay. Now, let's take a look at some similarities of free monoids and free commutative monoids. So, for example, we can define the length function by just extending the constant function that maps everything to 1. And we can also define a membership predicate by first fixing an element x. And we can define a unital map which takes an element y, and then it gives us the type x is equal to y. And with this, we can just extend the unital map, and then we get a membership predicate. But this similarity kind of breaks down when we're trying to define the head function. So for empty list or S list, this head function obviously doesn't exist. For singleton, it would be an equivalence. And when we are working with multi-element list or S list, well, for this, we can just take the first element. For S list, because xy is equal to yx, if we want to define the head function, then head xy would be equal to head yx. So the problem is now, which one do we pick? And we need more extra structure on A in order to define a head function. So we can kind of see how commutativity kind of enforce the idea of unorderless because we can't just pick an arbitrary element out of an unordered list, and we need more structure to do that, which kind of brings us to ordering and sorting. So consider the canonical map from free monoid to free commutative monoid. And the section to this canonical map would basically be picking a canonical representation out of the equivalent classes generated by permutation. And because it is kind of somehow imposing a canonical permutation on the unordered list, then it's only natural that sorting function would be sections to this canonical map. And we can show how sorting can be axiomatized from this point of view. So, well, what we proved informally was if A has a desirable total order, there's a well-behaved section, and if there's a well-behaved section, then A would be totally ordered. Well, the first part is very trivial to prove because we can just take, given a desirable total order, well, we can just do insertion sort, and this insertion sort will be our well-behaved section. This isn't surprising. What's more interesting is how we can turn a well-behaved section into a total order, so how we can construct ordering from sorting. So first, we define what a least element is. So this element of xs would be first applying the section s to xs, and then we just take the first element out of the resulting list. And we construct our relation. So we say x is less than equal to y if this xy is equal to x. And we can trivially prove reflexivity and symmetry and totality. But what about totality? And what about transitivity? So as it turns out that just by being a section alone, we can't actually prove transitivity. We need more constraints. So for example, consider this section. So basically what this does is that if the length of the list is odd, then it would just sort normally, otherwise it would just sort in a reverse direction. And this would violate transitivity. Well, it is a fed up section, but it doesn't do sorting, and it also violates transitivity. So in order to fix this, what we need to do is to add a constraint to the section that we're considering. So first, we define the notion of a sorted list. We say that a list is sorted if it is in the image of our section. And we give our first axiom of sorting, which is that a section satisfies its head list if, say, we have a list x cons xs, if x context is sorted, and then for any element y in this sorted list, then x, y should be sorted. So, and basically we prove that if a section satisfies this property, then we can prove that the order, the relation that we constructed would be would satisfy transitivity, and therefore it would be a total order. Now the next step would be trying to improve this to a full equivalence. So given a decidable total order, well, we can just construct a section by insertion sort, and insertion sort will obviously satisfy this axiom. And now, let's say we construct an order from our insertion sort. So does the original order that we started with, is it the same as the order that we constructed? And also, in the other direction, say we have a section S, we use it to construct a total order. Well, can we reconstruct the section back from the total order? And as it turns out that actually no, and because consider this section. So what this does is that it sorts a list, but then it will reverse the tail of this list. So if we take this section and also the insertion sort that it is based on, if we map it to a total order, then it would actually give us the same total order. So in order to actually get a full equivalence, we need to add another constraint which says that the tail of a sorted list should be also sorted. And with this, we arrive at our final theorem. So we have deck-thought odd, which is basically just a set of decidable total order on A. And we have sort A, which is the set of sections, the set of well-behaved sections on A. And also, we assume A has decidable equality. So what we prove is that these two are actually equivalent. So in other words, there's a decidable total order on A if and only if A has decidable equality, and also it has a well-behaved section. So given deck-thought odd, we can just use insertion sort, and then we can just do insertion sort, and then we will get our section. We can also prove that A has decidable equality, and given a section given a well-behaved section on A, we can just construct a total order as we've previously stated, and A would have decidable equality because because we assume A has decidable equality, this total order that we constructed will also be decidable. And to prove it's a full equivalence, so given a total order, we turn it into a section, and we turn it back into a total order. Well, because this xy is equal to x, if and only if x is less than or equal to y, then I mean this is trivial. But if we take a section, we turn it into total order, and then we turn it back into a section. Well, the proof is more complicated. First, because a section satisfies the first axiom is headless, we can use it to construct a total order. And then the way we prove it is to just define a very conventional witness for a sorted list. And the second axiom is tail sort would let us inductively prove that for any section S, the output of the section should be sorted according to this total order that it is constructed from. And now, in order to go from decidable total order to section, we can just do insertion sort. And because section and insertion sort both produce lists sorted by the same total order, so they must be the same. And finally, we answer our question, what's a correct sorting algorithm? Well, a correct sorting algorithm is basically just a section to the canonical map from free monoid to free commutative monoid, satisfying these two properties. And as a sanity check, we can make sure that our axiom for sorting is actually correct by showing how it relates to a conventional definition of sorted list. For example, take sorted for Coq, which is pretty much the same as what we defined earlier. And this diagram, we can basically prove that this diagram commutes. So given a well-behaved section S, we can define sort, which turns a list into an ordered list. And then what this diagram says is that if we first sort a list and then we forget the order by turning it into an S list, it would be the same as just forgetting the order directly without sorting. In conclusion, So we just developed new axiomatization for sort function by showing the correspondence between sort function, well-behaved section, and decidable total order. And in future work, it would be interesting to show whether all sections are defined in terms of well-behaved sections. So equivalently, does the existence of a section necessarily imply that there is a total order on A? And also, it'd be interesting to generalize a universal algebra framework from set to group point. But first, we need to figure out how to define a system of coherences. So yeah, that's it. Thank you.
Keep it on for the questions.
Oh.
All right, thank you. Any questions?
So, hello. Yeah, thank
Hi.
you very much for a very nice talk. Very interesting. I saw recently a specification of sorted of a sorting relation. I mean, which is sort of the other way around, to say it has to be anti-reflexive and transitive, and decidable. Would this change anything in for your specification if you use this for a specification of sorting relation? I mean, sorting with respect to anti-reflexive total order?
We tried that, but the thing is, we kind of ran into a lot of issues with decidability, and eventually we just decided that working with a reflexive order would just be easier. So that's the route that we took. We haven't re-investigated anti-reflexive order.
Okay, thank you.
More questions?
Can you show your two head and tail conditions again?
Sorry, do we mean this one? Or?
This is one of them, the tail sort, and then there's is head least or something.
Yeah,
Here you
this
have
one.
them both. Okay. I was wondering if these two conditions combined are equivalent to something like, if you have a sublist of a sorted list, then it's still sorted.
Yeah, but see, the problem with that is that defining what a sublist is gets really complicated. We tried merging it into one single axiom by just doing sublist, and it ended up first, the definition ended up being really complicated, and also trying to prove that insertion sort satisfy this property is just really annoying. So we just said, let's just split into two simple axioms.
Yeah, I can believe that. Thanks.
Okay.
More questions? Maybe I have a naive one then. So I think you did that in cubical lagda?
Yes.
Right? So did you need like the cubical aspect only for the definitions of like free monoids, or did you also use it in your proofs?
Well, we only kind of use the cubical aspect in defining free commutative monoids, and also, because cubical, we also define a universal property in terms of equivalences. For but the thing, other than that, we haven't really touched on any cubical aspects.
Okay, thank you. One last quick question. If not, let's thank Wing again.